Grounding grids are essential components of electrical safety systems, particularly in locations where sensitive electronic equipment is used or where human safety is paramount. Understanding the principles behind grounding grids, including the crucial aspect of spacing, is vital for ensuring their effectiveness. A grounding grid is a network of interconnected conductors buried in the earth. Its primary purpose is to provide a low impedance path for fault currents to return to the source, thereby facilitating the rapid operation of protective devices like circuit breakers or fuses. This, in turn, minimizes the duration of fault currents and reduces the risk of electrical shock hazards and equipment damage. The spacing between the conductors in a grounding grid is not arbitrary. It is a carefully considered design parameter that directly impacts the grid's performance. Several factors influence the optimal spacing, including the soil resistivity, the magnitude of fault currents, and the desired touch and step potential limits. Soil resistivity is a measure of the soil's resistance to the flow of electrical current. It is a critical parameter in grounding system design because it determines how effectively the earth can conduct fault currents away from the protected equipment and personnel. Soil resistivity varies widely depending on the soil composition, moisture content, temperature, and the presence of dissolved salts. Generally, soils with high moisture content and dissolved salts have lower resistivity, while dry, sandy soils have higher resistivity. Before designing a grounding grid, it is essential to conduct soil resistivity tests to accurately determine the soil's electrical characteristics. These tests typically involve injecting current into the soil and measuring the resulting voltage drop to calculate resistivity. The magnitude of fault currents is another key factor influencing the spacing requirements of a grounding grid. Fault currents are the large currents that flow during an electrical fault, such as a short circuit. The grounding grid must be capable of safely carrying these fault currents without exceeding its thermal capacity or creating dangerous voltage gradients in the surrounding area. The larger the fault current, the more closely spaced the conductors in the grounding grid must be to effectively distribute the current and minimize voltage rise. Touch potential is the voltage difference between the ground potential rise and the surface potential at the location where a person could be standing and simultaneously touching grounded equipment. Step potential is the voltage difference between 2 points on the ground surface that are 1 meter apart. Both touch and step potentials pose a risk of electrical shock if they exceed safe limits. The grounding grid design must aim to minimize these potentials to protect personnel from electrical hazards. The spacing between conductors in the grid plays a crucial role in controlling touch and step potentials. Closer spacing generally results in lower touch and step potentials because it creates a more uniform distribution of voltage across the ground surface. The relationship between conductor spacing and touch and step potentials is complex and is typically analyzed using computer modeling software. These software programs can simulate the flow of fault currents through the grounding grid and calculate the resulting voltage gradient. Engineers use these simulations to optimize the grid design and ensure that touch and step potentials remain within safe limits. Several industry standards and guidelines provide recommendations for grounding grid design, including conductor spacing. These standards, such as Institute of Electrical and Electronics Engineers Standard 80 Guide for Safety in AC Substation Grounding, provide detailed guidance on calculating touch and step potentials and determining acceptable limits. They also offer recommendations for conductor size, burial depth, and other design parameters. The primary reason for requiring specific spacing in grounding grids stems from the physics of current distribution in the earth. When fault current enters the ground through a grounding electrode, it spreads out in all directions. The current density is highest near the electrode and decreases with distance. The voltage gradient in the earth is directly proportional to the current density. Therefore, the voltage gradient is also highest near the electrode and decreases with distance. If the grounding electrodes are spaced too far apart, the voltage gradients around each electrode will not overlap effectively. This can result in high touch and step potentials in the areas between the electrodes. Conversely, if the electrodes are spaced too closely together, the effective grounding area will be reduced, and the overall impedance of the grounding system will increase. This can limit the ability of the grounding system to quickly clear fault currents. The optimal spacing represents a compromise between these two extremes. It aims to provide a uniform distribution of voltage across the ground surface while maintaining a low impedance path for fault currents. The Institute of Electrical and Electronics Engineers Standard 80 provides equations and guidelines for calculating the optimal spacing based on soil resistivity, fault current magnitude, and desired touch and step potential limits. In addition to the factors mentioned above, the presence of buried metallic objects, such as pipelines or underground cables, can also influence the spacing requirements of a grounding grid. These objects can act as secondary grounding electrodes and alter the distribution of fault currents in the earth. It is important to consider the location of these objects during the grounding grid design and to ensure that they are properly bonded to the grid to prevent the development of dangerous voltage gradients. The installation of a grounding grid is a critical process that must be performed carefully to ensure its effectiveness. The conductors must be buried at the specified depth and properly connected to each other using approved methods. The connections must be mechanically strong and corrosion resistant to ensure long-term reliability. After the grounding grid is installed, it is important to perform tests to verify its performance. These tests typically involve measuring the impedance of the grounding system and verifying that touch and step potentials are within acceptable limits. If the test results indicate that the grounding system is not performing adequately, corrective actions must be taken, such as adding additional grounding electrodes or improving the soil conductivity. In summary, the spacing between conductors in a grounding grid is a critical design parameter that directly impacts the grid's performance and safety. The optimal spacing depends on several factors, including soil resistivity, fault current magnitude, desired touch and step potential limits, and the presence of buried metallic objects. Following industry standards and guidelines and performing thorough testing are essential for ensuring that the grounding grid provides adequate protection against electrical shock hazards and equipment damage. Designing an effective grounding grid involves a detailed analysis of site-specific conditions and careful consideration of applicable standards and regulations. It is recommended to consult with qualified electrical engineers who have experience in grounding system design to ensure that the grounding grid meets the specific needs of the facility. Furthermore, regular inspection and maintenance of the grounding grid are essential to ensure its continued effectiveness. The connections should be inspected for corrosion and tightness, and the soil resistivity should be periodically retested to ensure that it has not changed significantly. Any damage to the grounding grid should be promptly repaired to maintain its integrity. Grounding grids are not just about safety, they also play a vital role in ensuring the reliable operation of sensitive electronic equipment. By providing a stable reference potential, grounding grids help to minimize electrical noise and interference, which can disrupt the operation of electronic devices. This is particularly important in facilities such as data centers, hospitals, and research laboratories, where sensitive equipment is used. In these environments, a well-designed grounding grid can significantly improve the performance and reliability of electronic equipment. The design of grounding grids has evolved significantly over time with the development of new technologies and materials. Modern grounding grids often incorporate advanced features such as chemical grounding electrodes and surge protection devices to further enhance their performance. Chemical grounding electrodes are designed to improve the conductivity of the soil around the electrode, thereby reducing the overall impedance of the grounding system. Surge protection devices are used to protect equipment from transient voltage surges caused by lightning or switching operations. These devices divert the surge current to ground, preventing it from damaging sensitive equipment. As electrical systems become more complex and sophisticated, the importance of effective grounding systems will continue to grow. A well-designed and properly maintained grounding grid is an essential component of any electrical safety program and is critical for protecting people and equipment from the hazards of electricity.